Okay, now I'm recording. That's great. Um, mhm. About the quiz. Okay, first thing is good news. I want to share. Pearson agreed to offer. Like, how many students are you? I thought 17. I talked to them about 17 students, and they sent me 17 codes to get into my lab for free. This is very good news. But I'm suspecting that there could be more than 17 now. So I'm gonna ask them again for a couple more. But I would ask you to quickly after this class go and register for my lab on Pearson. I send you the information. Okay. 2 students already registered. Maybe there's been more after I checked last time. On there you have the ebook for free, and you're gonna have the a lot of exercises that you can practice on. And I set up 3 homework already, so work on these homework. Quizzes will be similar to them. Okay, yeah. I think Behi and Faiz registered, if I remember right. Right? I don't remember seeing anybody else, but I urge you to go and do it ASAP. Alright, so okay, and I'm gonna keep recording more after this class. Right now we are in 2.5. My other, okay, before we start, I will also tell you that you're going to have your first quiz maybe on Saturday, could be Sunday, depending on your situation. Like if you have classes on Saturday or Sunday, we can postpone it to Monday. But first quiz is gonna be in one of these days: Friday, Saturday, Sunday, Monday. And I'm gonna send you the content of the quiz as well, which chapters, which sections you are going to be responsible for, and how can you get ready for the quiz. I'm going to set up a couple more homework questions, and you can work on these homework questions. You can ask me if you have any questions. As you know, homework actually is not mandatory, but I would recommend you to go over and do as many questions as you can, since quiz problems are going to be similar to them. Okay, sure. Okay, Mary. Alright, so let's start. So if you have any questions, let me know. So I said quiz 1 is going to be on one of these, and afterwards, following week, there could be a midterm, and then after that midterm there will be the quiz 2, and it's going to be, I think, the 5th week that quiz 2 will happen. We can, if we need, we can postpone it to the 6th week, and afterwards you're gonna have the final, and it's gonna be all over. Okay? Right. If you don't have any questions, I'm gonna start recording the lecture. Or talking about the lecture. Lecture, not recorded. It's gonna be recorded, but we are gonna start the lecture. Okay. I hope that this lecture is gonna be like question and answer, like the one we did last time. You can ask me your questions if you might have about the sections that we covered before, because I told you on Mondays I'm going to answer your questions. If you have any questions, any math questions, I can answer. If you don't have any math questions, then I can start continuity. Just let me know. Okay? Do you have any math questions before I start? You can write on the chat. It seems you don't have any questions, so let's go on. Let's talk about the continuity. Okay. And I also would like to emphasize that the lecture notes that are prepared by Thomas calculus are nicer, so you're gonna definitely see the difference. It's really good, so you're gonna enjoy it, you're gonna learn better. Okay, so what's continuity? Actually, you can consider roughly the continuity as, for example, we are gonna say a function is going to be continuous if you have the graph, if you can draw the graph of it by using a pen, okay, and then you will never take away the pen till the end of the graph. That's what the continuity is roughly. Okay? Yani kalemle çizmeye başladığınız zaman, mesela grafını çizdiğiniz zaman kalemi hiç kaldırmıyorsunuz. Sürekli kalem sonuna kadar o kalemle grafı çizebilecek durumdaysanız o sürekli bir fonksiyonun grafı demek. Okay, so that's just a rough idea, but that's true. Okay, so if you have like I'm going to talk about a graph of a function where the function is not continuous. Actually, it's not continuous at several points, and that way you're gonna understand this a lot better. Okay, so for example, this picture is a graph of a function. See, it's made up of several pieces. Like we have this piece, we have this piece, this and this piece. So you can consider like 4 pieces. And then between 0 and 1 it's continuous, so no problem. Between 1 and 2 it is continuous. Between 2 and 3 it is continuous. Between 3 and 4 it's continuous. However, it is not continuous at 1. The reason is there's a jump. You have to jump from 0 to 1 to continue, right? And at 2 it's not continuous either. Okay? There's another jump. Like you come here and you jump up and then come down and continue. At 3 it is continuous because there's no jumps, no broken graph. Okay? At 4 there's obviously a jump. Like you come down here and then you jump to get to this point. So by looking at the graph you can say easily that a graph is not continuous or not. So it is very obvious. But sometimes you don't have the graph. If you don't have the graph, then it's more difficult. So how are we going to? So last time actually we talked about one-sided limits. You might have seen the recording. What's a one-sided limit? We, for example, right limit, left limit. Right limits, you're going to have a limit from the right, but you don't care about the left. Okay? Or a function has a limit from the left means it has a limit, the value as x approaches to c. The limit of that function is finite. It exists. We have similar notion for continuity as well. We have right continuous functions, left continuous functions. But before I talk to you about that, I want to tell you something about being continuous at C. So what does it mean being continuous at C? So actually there are 3 requirements for that. First of all, first condition is the limit as x approaches to C of f of x, it has to exist. Okay, this is number 1. Second condition is the value of the function is defined at the point C. Okay, f of c is defined, it's a number. The third condition is this limit is going to be the same as the value of the function at c. Okay, alright. Alright, so let me hide the conversation here. We may not need it. So this is continuity. So in order to, okay, what is it again? A function is continuous at c if we have a limit as x approaches to c, f of x, it exists. the value of the function at C is finite, and this, they are both equal to each other. So 3 conditions. Okay. Right continuity at C, you can define it similarly. So there are 3 conditions again. First of all, you're going to have the right limit exist. Limit exists means it's a finite value. And then the value of the function is defined at that point. F of C is defined, it's finite. And then the right limit is equal to the value of the function. This is the 3rd condition. For the left continuity, it is similar. You want to make sure that the left limit exists. You want to make sure that the value of the function at C exists, and they are equal to each other. This is the 3rd condition. Okay. Pictures are always good. So the blue one is our function f, and then we have the point C. We are interested in understanding the continuity from the right and continuity from the left at C. So if you have the two-sided continuity, continuity from right and continuity from left, okay, then and if they are equal, then there's the function is continuous at that point. Okay, so let's get this function. This function is this function continuous on the interval -2 to 2? That's the question. As you see, this is the graph of a semicircle. Y is equal to square root of 4 minus x squared. Actually, everybody knows how to write equation of the square. Main circle, sorry. Circle is x squared plus y squared is equal to 4 in this case. But we are interested in the top half, top semicircle. Okay, upper semicircle. So we have to choose y, positive part, plus square root of 4 minus x squared is the equation of that. Now, this function is continuous, of course, on its domain, because if you start drawing it, and you will never remove your pen till the end. Okay? So this is a continuous function. Okay, no problem. Let's get this function. This function is actually called step function, unit step function. That's why we have the name as u of x, unit step function. What does it mean? It's like a step, right? Stair. Like this is the first stair, second stair, right? Staircase. So this is called step function. This function is not continuous at 0 because left limit and right limit, they don't agree. Okay, because the limit doesn't exist at 0. And limit, one of the conditions to be continuous is that limit has to exist at that point. So here the limit fails to exist because left limit is not the same as right limit. Right limit is 1, left limit is 0. 0 is not equal to 1. So when you have that, when you have such step or jumps, we call it jump discontinuity. This is a special discontinuity because in some questions you're going to be asked what type of a discontinuity does this function have at this certain point, and you should be able to say it's a jump discontinuity or infinite discontinuity. Okay, you should be able to say that this is the jump discontinuity. Here's the continuity test that I mentioned actually when I was giving the definition. A function f is continuous at a point c, x is equal to c, if and only if it meets the following 3 conditions. F of c exists, the value of the function at c exists. Okay, of course we want to make sure that c lies in the domain of f. Second, the limit as x approaches to c of f of x exists, right? Which in other words, f has a limit at x is equal to c, or as x goes to c, sorry. Not at, as, okay? Limit means x approaches to c, not x is equal to c, okay? And then third condition is this is equal to that, right? This limit has to equal to the value of the function at c. Okay, discontinuity test is very important, and I want you to know that. There's this greatest integer function. It is like too many stairs. Okay, too many steps in here. Okay, so how many discontinuities do you see? For example, at -1 there's a discontinuity here. At 0 there's a discontinuity here. Jump. At 1 there's a discontinuity, there's a jump. At 2, so how many jump discontinuities do we have? We have infinitely many, because we have -1, 0, 1, 2, 3, 4, 5. It's gonna go forever. So we have jump discontinuity. Okay. But as you remember, okay, there's a question maybe here. Is there a question? Yeah. Iran, what did you mean by same? Right, it's all the same, right? So we have the right, we can also see the right continuity and left continuity here. For example, in this example is good to remember, because we have points where we have right continuity is okay, but left continuity is not okay. For example, at 1, if you look at from the right, we have the right limit is 1, and the value of the function at 1 is 1. So we have right continuity. In other words, we have one-sided continuity, which is from the right, but we don't have the left continuity. So it's going to be the same for all these points. Okay, so this is a good example to remember. We have all sorts of examples we have right now. Okay. All right. What is this example? Let's analyze each example here. We are focusing on one point. So we are going to look at 0, x is equal to 0 for each. Okay, let's get x is equal to 0 for each example we have here. Okay, how many examples do we have? 1, 2, 3, 4, 5, 6 examples. Okay, let's look at the first example. The first example at 0, we don't have any problem. We have the continuity here, right? No jumps, nothing. For b, at x is equal to 0, the function is not defined. So which continuity test fails? Which of the continuity test parts fail here? Let's go to the continuity test. F of c exists. The first condition fails, like f of c exists is not true here. Look, f of 0 is not defined here. If you look at c, f of c, which is f of 0, is defined, which is 2. However, okay, the value of the function and the limit at 0, they don't match. So which condition fails? Condition 3 fails, because the value of the function is f of 0. F of 0 is 2, but the limit is 1. Limit as x approaches to 0 is 1, right? It was 1, right? Let's check. Yeah, it's 1. So they don't agree. So the third condition in the continuity test fails here. Okay, this is the first condition fails. Third condition fails here. That's why it's discontinuous. Here, the limit doesn't exist. It's 0. So it's the condition 2 fails here. So these are examples of where the conditions fail. Each condition fails. So it's good to remember such examples. Okay. E and F are different. Okay, I want you to make sure that you understand B, C, D. Okay, these are okay and simple. All right. E, on the other hand, this is the graph of 1 over x squared. 1 over x squared is looking like this. So let's try to understand this function for the future references, because we may need this function again. This is a function where as x approaches to plus infinity and minus infinity, it goes to 0. So therefore the graph is going to get close to 0 as x approaches to plus infinity, and the graph is going to go to 0 as x approaches to negative infinity. On the other hand, as x approaches to 0 from the right and from the left, it goes to infinity. Look, right? It becomes very big, because as x approaches to 0, x is very small. 1 over a very small number gets very large. Okay? So this is our function, f of x is equal to 1 over x squared. And the question is, we are focusing on 0. So is the function f continuous at 0 at all? What do you think? Is it continuous at 0? And if it is not, why not? Which condition fails? Like we have continued to test. First of all, you have to decide whether the function is discontinuous or not at 0. So can you tell me whether the function is it continuous at 0? Can you write your names in the chat? Is f continuous at 0? Can you write your answer, please? Okay. You said no, it's not continuous at 0. But if you say so, which condition fails? Is it the first condition in continuity test? Is it the second continuity condition in continuity test, or the third one fails? Which one, Barish, you think? Why is this not continuous? Which test condition is not satisfied? Can you tell us? The first condition was the value of the function. It's first one, teacher. Yeah, the value of the function at 0. Does it exist? Not at all. Okay, the first condition fails. Actually, more conditions fail. The limit as x approaches to 0 is infinite, and it's an infinite value, and f of 0 is undefined. So yeah, first condition is enough. First condition is not satisfied. Because of that, it is not it's not continuous. Actually, we have infinite discontinuity here, right? Do you see? We call it infinite discontinuity if you have that. Okay, and then the last example. First, I have a question for you. This is sine 1 over x. This is a very well-known function. This is an oscillating function. Okay, this oscillates as x approaches to 0 from the right and the left. Okay, so the question is this function, is this oscillating function continuous at x is equal to, or as at x is equal to 0? What's the answer? What's your answer? And why? Can anyone say? Do you have an idea about that? Or what is your guess? Is this function continuous at 0? And what is the reason? Oscillating means, let me explain it to you. Oscillating means, maybe I should tell you oscillating, you don't know that. Oscillating means this graph is going to go up and down, up and down, up and down, up and down, infinitely many times, uncountably many times as you get close to 0. So it's through both sides, okay? It's going up and down, up and down, up and down. So what could be the problem? So I'm telling you it's not continuous at 0, but what could be the reason? What is the value, what is f of 0? Do you know? Do you know f of 0 here? I need an answer. F of 0 is not defined. That's right, because 1 over 0 is undefined, right? Sine 1 over 0 is going to be undefined as well. So f of 0 is not defined. And also the limit as x approaches to 0 doesn't exist either. So actually in this case, all three conditions in the continuity test, they fail to happen. Okay? Limit doesn't exist, and the value of the function is not defined at 0. And of course, since the limit doesn't exist, the value of the function is not equal to that. So all conditions fail. Because of that, it is not continuous at 0. Okay? Thanks, Barish. Okay. And now we have another function. This is also a well-known function. So the functions we have seen so far, okay, they are the simplest functions that you should be aware of. Okay? In the future, we are going to make them more complicated, but these are the simplest ones. But when you know the simple functions, you can always create the complicated functions from them. Again, we are focusing on 0. For the rest of the numbers, for example, x bigger than 0, it is a continuous function. For x less than 0, it's a continuous function, right? No jumps, nothing. So everything is good. But only at 0 there's a problem. At 0 it's not a continuous function. First of all, 0 is not in the domain of that function at all. So the function is not defined at 0. So first condition fails in the test. For the continuous functions, of course, we can do some operations, like we can add them, take the difference, multiply them, take the ratio, raise it to a power, take the roots, nth roots, etc. So these are the operations we do, and the question is, when we do these operations, and if you know that the two f and g are both continuous functions, and if you do operations like that, the function that we get after we do these algebraic combinations, operations, the resulting function, is it still continuous? Actually, we are all giving the positive answer to that. But number 5 is the one that you have to be careful about, because if you take the ratio f over g, you want to make sure that at x equals to c, g of c is not 0. Because if it is 0, then it's going to make it undefined. This is the only condition. If you have g of c is not 0, then the quotient, the function as you take the ratio of f and g, is going to be a continuous function. If you take f, which is itself a continuous function, if you raise it to the nth power, then it's going to be a continuous again. For example, y is equal to x is a continuous function, x to the n is a continuous function as well. To give an example. For example, let's say y is equal to x is a continuous function, square root of x is also a continuous function, or cube root of x is also a continuous function, okay? Let me go and get some water, okay? Give me just 1 sec. Okay, so we have a theorem which says actually if you have two functions and if you compose them, then the composition of the functions is continuous at the point C as well. Of course, we require f to be continuous at C and g to be continuous at f of C, because you know composition of functions one inside another. So you have that rule. Here is f, here is g. So these pictures are really nice for you actually. F is continuous at c, look at that. And we have the value of c, and then we compose f with g. And g is continuous at f of c. Then this G compose F is going to be continuous at C. So these are nice problems. So you can just remember composition of two continuous functions is continuous is good. Is enough. Okay? Alright. So what is this example? This example actually is composition of two functions. We have x sine x over x squared plus 2. This is a function and you compose it with absolute value of x. Absolute value function is continuous. And then this x sine x over x squared plus 2 is continuous because the denominator is never ever 0. So the composition of the two continuous function is continuous. This is a nice example here. Limits of continuous functions. So the limits, just one sec.
Şarjını aldı bunu.
Tamam alsın, tamam. Okay, sorry about that. Doorbell rang, so I had to go and open the door. Sorry about that. Okay, limits of continuous functions. Let's say we know G is a continuous function, and let's say we don't know much about f, but we know that as x approaches to c, f has a limit, and we know that G is continuous. So this one is weaker if you compare, like the f is not continuous anymore. Okay, but you know that G is continuous. So limit of G compose f is going to be, you would be able to move this limit inside the parentheses. So whenever you have a continuous function, G is continuous, you can always move this inside the function as long as you know that G is continuous. That's what this theorem is telling you. Okay, and that's a big luxury actually, you keep moving in limit inside the function. Okay, this is going to help you big time when you're computing limits. Okay, so we have this well-known intermediate value theorem, IVT in short. Okay, it says intermediate value theorem for continuous functions. So from the title, what do we understand? We understand that this theorem is okay for continuous functions only. So the first condition in this theorem is that the function that we deal with, which is f, has to be a continuous function. This is the first thing we understand. And we are going to be dealing with a closed interval, okay, a to b. So our function f is supposed to be a continuous function on a closed and bounded interval a to b. Okay. And then fix any points between, okay, so since this is a, this is b, the image is f of a, the image of b is f of b, and then in the theorem it says pick any point between this f of a and f of b, which is a y value, right? Pick any point. And this theorem says, intermediate value theorem says, you will be able to find a c that's in between a and b such that this c is going to go to that point. Okay, for each point here in between, you will be able to find the x value that's going to go to that. So that's the theorem. Maybe it may not, you may say, oh, this is nonsense, where am I going to use it, etc. But you will see that this theorem is useful, very, very useful. Okay? So, to repeat again, f is a function, f is a continuous function. It's a continuous function on a closed and bounded interval. And look at the image of a and image of b. If you fix any point in between f of a and f of b, it doesn't matter which one. you will always find a value c that's in between a and b that's going to go to that y naught value. Okay, that's it. Okay, let's see where we can okay, this example actually tells you that the previous theorem cannot happen if the function is not continuous. So this function is not continuous, as you see, right? The interval is 1 to 4. It's a closed and bounded interval. The function is not continuous. So pick a point. Okay, what's the image of 1? Image of 1 is 0. What's the image of 4? 4 is 3. So pick arbitrary points in between 0 and 3. Let's pick 2.5. Go back to 2.5. And you won't be able to find any c value, any x value that's going to go to that point, right? So intermediate value theorem will only work when f is continuous. This example shows you that. Okay. So let's see. Okay. So where do we use this intermediate value theorem? We can use this intermediate value theorem to locate a zero of a function. Okay, the first picture is the graph of a function x cubed minus x minus 1. Okay, this is the graph. Do you see a zero of this here? There's a zero, right? And this 0 is between what? 1, 2, between 2 and 3, there's the 0 of this function. 0 of a function means at that point, f of, let's say call it c, f of c is equal to 0. Okay? So we know that c is between 2 and 3. Okay? I mean, just a sec. No, I made a mistake because this is 2. I'm so sorry. This is 2. I just thought that this is 1, 2, 3. No. This is 2, so this is 1, so it's going to be between 1 and 1.5. Sorry about that. So it should be between, this is 1, this is 2. So this 0 is between 1 and 1.5. Okay? If you enlarge this area and you get this picture, in part B you enlarge it. See? Okay, this is between 1 and 1.6, and the 0 is somewhere in between, and you enlarge it a little bit more. Okay, I mean, enlarge it means zoom in. If you zoom in, you're going to see that the 0 is between 1.32 and 1.33, between these two numbers. And zoom in more, you're going to see that this 0 is between these two values. So you can ask, what's the relationship between intermediate value theorem and the 0? Excuse me. I think we should have an example on that. Let me see. There's a relationship. Okay. This is example 11. It's not in front of me right now. This is about a 0. This is approaching finding the 0 of a function in a different way. Like, for example, if you want to find a 0 of this equation, square root of 2x plus 5 plus x squared minus 4 is equal to 0. So if you are interested in finding a 0 of this expression, of this equation, and in example 11 it says, oh, we can separate it into two functions, which is y is equal to square root of 2x plus 5 and y is equal to 4 minus x squared, and then we draw them. Okay, so this is a parabola. We can draw this, and this is the root function. Okay, and then we can draw this too. This is like we can draw the graph of square root of x, and by using the square root of x we can draw that, and the intersection point is going to be where this equation has a 0. So this is locating where the 0 is. Okay, this idea. Let me see. Okay, now we are going to be talking about something else. Okay, this is new now. We don't work on intermediate value as much, but we should solve some problems about intermediate value theorem. In my coming lectures, I will solve some other problems for you to practice, where we use it, etc. I can solve some problems from the homework question as well, so that you understand it better, okay? But right now I'm going to be talking about something else. We jump to, you should remember that intermediate value theorem is related to finding the zeros of some equations, okay? I will give you some examples on the homework questions in our next class, in my next recording. Now, so here what do we say? So sometimes I want you to look at this function sine x over x. Sine x over x, if you can consider negative pi over 2 and pi over 2 at x is equal to 0, okay? Anybody remembers the limit of sine x over x? We didn't say that, but sine x over x, actually in my recordings, one of the recordings, I think we said that. Sine x over x is a special expression, function, and as x approaches to 0, this goes to 1. Okay, so however it goes to 1. Look at that, the limit is 1, but at x is equal to 0 it's not defined. So this sine x over x is a weird function. At x is equal to 0 it is not defined because x is in the denominator and it makes the denominator 0, but as x approaches to 0 the limit is 1. Look at the limit. You go from the right, you go from the left, the height is 1. Okay, and this figure on the right hand side, it says, okay, sine x over x may not be a continuous function, but I can redefine it and make it a continuous function. Okay. Okay. Hi, Merve. How am I going to do? I'm going to define a new function. Okay, we call it extension of this function. So we extend this function to be a continuous one. How would you do? You're going to say my new function is going to be sine x over x whenever x is never 0, and it's going to be 1 whenever x is 0. So you define it in a way so that this new function, which is an extension of this function, is a continuous function. So you are creating continuous functions from discontinuous functions. So this one is a discontinuous function at 0, but we extended it in a way that it becomes a continuous function. So this is also an important notion that you guys need to know. So, okay. We call it actually removable discontinuity. This kind of discontinuities we call them removable discontinuity. So there are actually how many discontinuity types? 1, jump discontinuity. 2, infinite discontinuity. 3, removable discontinuity. So for removable discontinuity is it's a function that you can fill in this gap and extend it to a continuous function. So you are removing the discontinuity. So this type of discontinuity is called removable discontinuity at x is equal to 0. And now we removed it and made it or created a new function that's continuous out of that. Okay? Do you want to see another example like that? Like we are going to have a function which is going to have the removable discontinuity, but since it is a removable discontinuity, we are going to remove the discontinuity by redefining it, extending it to a continuous function. Okay, here is the function. This is you look at A. In A, this is the graph of the function. Okay, let's plug in 2. At 2, this is 2 squared, 4 minus 4 is 0. So at 2, this function can never ever be defined because it makes the denominator 0. So at x is equal to 2, we have a discontinuity because the function is not defined at that point. So the first condition in continuity test fails. But I'm telling you that this is a removable discontinuity. I can remove this discontinuity by filling in this gap. So I'm going to define it in a way that I'm going to say my new function is going to be this function outside of 2 for all points other than 2. My function is going to be this. But for x is equal to 2, my function will take the value 1.5 over 4. 5 over 4, okay? But how would I know 5 over 4? You can do that by actually simplifying it. Look, if you, this is a polynomial over polynomial, which we call them rational functions. If you have rational functions, which is a polynomial over polynomial, what you would want to do is you would want to factor it out. So let's factor this out. The top part, the numerator. X minus 2 times x plus 3, okay, is the top part. X minus 2 times x plus 3 is the numerator. And the denominator is x minus 2 times x plus 2. So x minus 2's we have in the numerator and the denominator, they cancel each other. After the cancellation, I have x plus 2 over x plus 3 over x plus 2. This x plus 3 over x plus 2 is not discontinuous at 2 anymore, because we got rid of the factor which was x minus 2, which was causing us a problem at 2. So we are gonna say our new function actually could be defined like this, or you could say this function whenever x is not 2, but at 2 the value is going to be 5 over 4. Put it 2 here. 2 plus 3 is 5. 2 plus 2 is 4. 5 over 4, that's how we get the 5 over 4. Okay? So this is the continuous extension. This function is the continuous extension of this function. They look similar, the functions look similar, but they are not the same functions at all. Okay? I hope you understood. Did you understand this example, this last example? This type of questions are very standard. Like you would be expected to learn, to know such examples. Okay? To pass this class. Yes. Definitely right, Yiğit Emre. On the graphs, it looks easy, but you should know. For example, I could give you in the midterm, I could give you a similar rational function. You should know that you are going to factor it out and do the simplifications and get a function like that. And this is going to be the extension of this function, continuous extension of this function. As long as you know how you should proceed, then your life is easy. Okay? Okay. section 2.6 is about infinite limits and asymptotes. Okay, maybe in high school you heard of asymptotes, and if you're in your previous classes you heard of that. Okay, limits involving infinity. Okay, let's understand it. This function you are familiar with, and you should be familiar with. Okay, y is equal to 1 over x. In my previous classes, one of the students said this is like a butterfly. You should remember this graph because it's easy to forget. So if you remember this like a butterfly example, so one of my students named it butterfly function. Okay, 1 over x is like a butterfly, and you can remember this graph. Okay, this butterfly example, 1 over x. Okay, so what happens to this as x approaches to plus and minus infinity? We are interested in, because we are interested in infinite limits. So what happens as x approaches to infinity? As x approaches to infinity, so x is getting very, very large. So 1 over a very large number gets very small. So it's going to go to 0. Similarly, as x approaches to negative infinity, so negative infinity is actually very large on the negative side. Okay, although it's the smallest of them all, but 1 over of that is going to be getting close to 0. Okay, it's going to get close to 0. Therefore, the picture is like a butterfly here. Okay, so now this is the first time we are talking about limit as x approaches to infinity or negative infinity. Okay, these are epsilon delta definitions we are going to skip. I don't want you to learn those because it is too much for you. Okay. All right. So here theorem 12 says all the limit laws in theorem 1 are true when we replace limit x goes to c by limit x goes to infinity and negative infinity. Okay. Yeah. So we have the limit laws, right? Addition of the functions, subtraction of the functions, etc. Ama gene kesik kesik mi geliyor acaba? Ha, iyi. Arada bir gidecek, böyle gidiyor. Yani yapacak hiçbir şey yok. Ben kayıt yaparken de gidiyor. Ama benim kayıtlarım tam full kayıt yapıyorum. Başka bir şeyden kayıt ettiğim için. Yani recordingler tam olacak. Diğer hani duymadığınız yerleri oradan artık yapacaksınız. Ama yani böyle bir saat sonra, bir saatte bir böyle bir gidiyor. Ama siz gene sesim gelmediği zaman söyleyin. Ara veririz falan. Bir şey yaparız. Öyle yapalım, tamam. Neyse, gelmişken devam edelim. Vakit kaybetmeyelim. Ben kaydıma bakıyorum bir saniye. Okey. Kaydediyormuşum, tamam. Şimdi şu ana kadar olan yerlerden sorunuz var mı? Türkçe sorabilirsiniz. Çünkü share yaparken upload edene kadar Türkçe konuşabilirsiniz. Hani upload yapamadım henüz. Sorularınız varsa soru sorabilirsiniz. Kafanızın karıştığı yerler varsa sorabilirsiniz. İngilizce de sorabilirsiniz. Yani bir fark etmez. En azından vakti değerlendirmiş oluruz. Tamam, güzel bir soru Barış. Şimdi onu Türkçe açıklayayım isterseniz size şu gelene kadar, çünkü PowerPoint slide yüklenene kadar vakit geçecek çünkü. Şimdi kere ilk önce size verilen fonksiyonun şeye karar vermeniz gerekiyor. Yani elinizdeki fonksiyondaki discontinuity removable mu değil mi ona karar vermeniz gerekiyor. Ona nasıl karar vereceğiz? Genelde candidate'ler işte rational function'lardan geliyor. Hani polynomial over polynomial'lardan gelecek. Ve denominator'ı yani paydayı sıfır yapan fonksiyonlar genelde removable discontinuity candidate'ler. Neden aslında candidate'ler? Çünkü biz şimdi polynomial over polynomial olduğu için o polinomları biz factor'larına ayırıyoruz. Çarpanlarına ayırıyoruz. Ve aynı çarpanları sadeleştirince o bize discontinuity'ye sebep olan kısım var ya, o kısımlar uçup gidiyor. O yüzden o geriye kalan yani deminki örnekte x-2 vardı. Factor yaptık. Payı da paydayı da çarpanlarına ayırdık. Ondan sonra x-2 vardı ikisinde de. Onlar x eşittir 2'de 0 yapıyordu paydayı. Onları cancel ettiğimiz zaman kurtulmuş olduk ondan. O x eksi 2'yi cancel ettiğimiz zaman hem payda da hem payda kalan şey aslında sürekli fonksiyon. Yani 2'de sürekli olan fonksiyon. Aslında bu bulduğumuz fonksiyon bizim extension'ımız. Bir önceki rational function'ın continuous extension'ı. Diyebilirsiniz cevabınıza. 2 çeşit cevap yazabilirsiniz. Onu demeye çalışmıştım ben. Aslında continuous extension'ı şöyle ifade edebiliyoruz. Bir, piecewise şeklinde yazabiliriz. Nasıl? İşte yeni fonksiyonumuzun adı g olsun. Hani extension'ımız. G fonksiyonu eşittir. İlk başladığımız f fonksiyonu whenever x is not 2 ve whenever x is 2, 5 over 4. G fonksiyonu eşittir 5 over 4. Bu bizim continuous extension'ımızda yazdığımız bir yöntem. Ama biz aynı zamanda g'yi şöyle yazabiliriz. G'yi hani o sadeleştirmeyi yaptıktan sonra kalan fonksiyon vardı ya. O fonksiyon aslında continuous extension'ı. Tamam mı? Yani iki çeşit cevap verebiliriz böyle. Öyle çeviriyoruz. Yani either piecewise function gibi yazıyoruz ya da o x eksi 2'leri sadeleştirdikten sonra kalan kısım bizim cevabımız oluyor. O kadar. Anlaşıldı mı? Barış, başka sorunuz var mı orada? Ben şu sayfalara gitmek istiyorum ama teker teker çok zor oluyor ya. Neden öyle? Daha hızlı bir şey yok muymuş? Enteresan. Tüm slaytların üzerinden geçmemiz gerekiyor. Yani burada bir zayıflık var. Aslında Teams grubuna söylemek lazım. Ya da var, ben bilmiyorum. Daha 27. sayfadayız. Enteresan. Kim başka bir yerde yazabiliyor muyum ki acaba? Ya da yazmama izin vermiyor. Neyse. Bekleyeceğiz. Geçerken sorunuz olursa söyleyin. Cevaplamaya çalışırım. Stop. Something is wrong. Okay. Sorry about this delay. For some reason, this happened. Now I'm with you, and we can talk about the limits as x goes to infinity, positive or negative infinite. So this is a very well-known example, as x goes to plus infinity and minus infinity. So yeah, all the limit laws applies here. Let's see. Okay, now I want you to look at the blue color, the graph, blue color. So you are not expected to draw this yet. This function, this is a polynomial over polynomial, which we call rational function. Okay, this is already drawn, and look, the red one, we will call it actually asymptote, the horizontal asymptote. So how are we going to find it? We are going to look at the limit of this function as x approaches to plus infinity and minus infinity. And when you take the limit as x goes to infinities, one of the infinities, if you find a value, if you find a number, that number is going to be your horizontal asymptote. Look, the limit of this as x approaches to infinity is 5 over 3. How do we know that? We can factor out x squared here. We have 5 left plus 8 over x minus 3 over x squared on top. And we can factor out x squared here. We get 3 plus 2 over x squared. And then x squares are going to cancel each other. And then we let x go to infinity. And we have 8 over x here goes to 0. 3 over x squared goes to 0. 2 over x squared goes to 0. So we have 5 over 3 left. So the limit, which is y is equal to 5 over 3, is the limit of this as x approaches to plus infinity. You are going to get the same limit as x approaches to negative infinity because you are taking the square of that. So if you square a negative number, you get a positive number. So the answer is going to be the same. But one of them is enough, actually. Either, but it's better to check what happens to this function as x approaches to plus infinity and minus infinity. Ay su buz koyar mısın? Okay. Sorry about that. Okay, we have a little accident here with my little boy. Okay, anyways. Alright, so let's look at this. So we are interested in this function, and we are interested in the limit of this function as x approaches to plus infinity and minus infinity. Okay, as x approaches to plus infinity, what happens to this function? Actually, if you look at the graph, it is easy. It goes to 0. And this is obvious because look, the degree of the denominator is bigger than the degree of the numerator. And this is going to tell you as x gets very large, since the power is bigger than the power here, this is going to go to infinity a lot quicker. So this is like 1 over infinity, so it's going to go to 0. So this is kind of obvious. How about as x goes to negative infinity? It is a similar situation here. Actually, it's going to go to 0 too. So in other words, y is equal to 0 is a horizontal asymptote. So now we just learned how to find the horizontal asymptote of a graph. You just need to look at the limits as x approaches to plus infinity and minus infinity. Whatever you found as a limit value, in this case we found y is equal to 0, so this is going to be your asymptote, horizontal asymptote. Okay, that's the idea. Here's the definition. So we are going to say a line y is equal to b is a horizontal asymptote of the graph of the function y is equal to f of x if one of these limits is taking the value b, right? One of these limits is b, right? Either x goes to infinity, it is going to be b, or x goes to negative infinity, it's going to be b. One of them is enough, as I told you before. Sometimes this example is just a little bit different. Look, as x approaches to plus infinity, the limit is y is equal to 1. So we have one horizontal asymptote, but we have another horizontal asymptote. We got the other one as x approaches to negative infinity. So this type of things happens. So it's always good to check both of the limits. As x approaches to plus infinity, what happens? And as x approaches to negative infinity, what happens? If either case you find a finite value, sometimes they are the same, sometimes they are different. Doesn't matter. Even if they are different, then you have two asymptotes, horizontal asymptotes. If they are the same, you have one single horizontal asymptote. Okay? Alright, so this is a nice example. But you can ask how we found the limit as x approaches to plus infinity, right? This is a nice question actually. Whenever x approaches to plus infinity, this absolute value of x is going to be positive. So this is like x cubed minus 2, x cubed plus 1, because x is positive, so the absolute value is positive. So the degrees are the same, so the limit is 1. This is obvious. What happens when x goes to negative infinity? The absolute value of x is, when x goes to negative infinity, it's negative x. So this is going to be, you're going to get x cubed minus 2 in the numerator, and negative x cubed plus 1 in the denominator. So look at the degrees. The degrees are going to be the same, but the signs are different. Plus 1 here, minus 1 here. So if you divide plus 1 by minus 1, you get negative 1. So that's why we have y is equal to negative 1. Okay, that's how we found the limit. If you may have any questions about this, let me know. Let's look at this weird function. So there's an oscillation here too. Look, it comes down here, goes up, and oscillates, and gets very close to 0, and then oscillates again and goes up like this. Okay, this is y is equal to x sine 1 over x. So we are interested in whether there's any horizontal asymptote. So we need to look at as x goes to infinity. Look, how are we gonna find the limit of this? Is interesting. Okay, I wish I could write here, but it doesn't allow me to write. Maybe I can try this. Look, I can. I'm gonna show you. Okay, the limit of this. After we finish these slides, I'm gonna open up the whiteboard and I'm gonna show you that. Okay, the limit of this is 1 as x goes to plus infinity. It is 1. I'm gonna show you. Maybe some of you already got that. Let's skip this example. This is easy. Why? Look, as x goes to plus infinity, sine x over x. Okay, sine x is bounded. Alright. Sine x is bounded. 1 over infinity goes to 0. This is going to go to 0. Because sine x can never be bigger than 1. Okay? And can never be less than negative 1. So, this thing is bounded by 1 over x. But 1 over x goes to 0 as x goes to infinity. So this is going to go to 2. Okay? This is a nice example too. So this is getting harder, of course. But I want to talk to you still so that you have some idea about that. Our function could be like x squared minus 3 over 2x minus 4. So the degree of this is bigger than the degree of this. So if you have that, you do the division, long division, right? You remember. You divide this by that. If you divide this by that, you get x over 2 plus 1 over 2x minus 4. If you don't remember long division, you can ask me and I can explain it to you in a separate class, okay? How we divide this. You can say, for example, page 88, figure 257, I don't understand how you do that. Then I can find ways to write it down and share it with you, okay? The explanation. So you just need to tell me if you have any questions like that. This is a new type of asymptote which we call oblique asymptote. When the degree of this is bigger than this, you have x over 2 here. Look, x over 2 is the oblique asymptote here. On the other hand, okay, we have a vertical asymptote which is x is equal to 4 over 2, which is 2. No horizontal asymptotes here. Anyways, so I'm going to skip this. I'm going to say this much about that, okay? Okay. So by infinite limits, so x goes to infinity is different than having infinite limits. Infinite limits means the value of the limit is infinite. For example, y is equal to 1 over x when you approach to 0 from either side. Alright. If you approach from either side, then it's going to go to plus infinity. Alright, just a sec, I am arranging the recording, double checking the recording, okay? Everything is fine. So two things we learned. One, what happens as x goes to plus infinity and minus infinity? This is when we get the horizontal asymptote. Number two, is there any x that's gonna give us the limit to be plus infinity or minus infinity? So this example is not type 2. So when x approaches to 0 from the right, the limit goes to plus infinity. If x approaches to 0 from the left, the limit goes to negative infinity. So the value of the limit is infinite now, okay? We call such limits as infinite limits. We call this one-sided infinite limits because one side of 0 it is plus infinity, other side, which is the left side, it is negative infinity, okay? Okay, let's look at this one. This is kind of shifted function of the previous butterfly example, right? This is a butterfly too, but this asymptote is shifted to the right by 1 unit. Okay, so what is the infinite limit here? As x approaches to 1 from the right, we have a plus infinity here. As x approaches to 1 from the left, we have the negative infinity here. Okay, we have another one. This is the function 1 over x squared. This is a nice function too, you should remember it. Okay, this is not like butterfly anymore. This is like volcano, right? We can call this volcano type. This is like there's a volcano and the lava is gonna come out here, right? You can just imagine that. This volcano example, in this volcano example, as x approaches to 0 from the right, the limit goes to plus infinity. If x approaches from the left, it goes to plus infinity too. So right and left limits are the same. So we can say maybe limit as x approaches to 0, the limit is actually plus infinity. Okay? Okay, we don't want to talk about the epsilon data definitions. We are going to skip that. Okay. But we come back to butterfly example again. In this butterfly example, how many asymptotes do we have? We have a horizontal asymptote, which we find as x approaches to plus and minus infinity. And we have vertical asymptote, which we have as x approaches to 0 from the right or from the left, okay? Whenever you have infinite limits, you get the vertical asymptote. Okay, x is equal to 0 is a vertical asymptote here. Okay, y is equal to 0 is a horizontal asymptote. So what's the vertical asymptote then? What's the definition? So first of all, vertical asymptote is a line. X is equal to a line. And we are going to call x is equal to a as a vertical asymptote if either the right limit is an infinite limit or the left limit is an infinite limit as x approaches to a, right? From the right or from the left. So this is enough. You just check one-sided infinite limits, and if you get one-sided limits and if you get an infinite limit, then you ready to go. So it's a vertical asymptote, okay? That's the only thing that you need to check. Let's do some examples. Here's the graph, here's the function. Y is equal to x plus 3 over x plus 2. To make it easier, we just divide this by this and we get 1 plus 1 over x plus 2. Okay? Actually, you can say this is a butterfly function again, but the shifted one towards left by 2 units. Okay? And to north by 1 unit, shifted north by 1 unit, shifted west by 2 units, right? Okay, it's shifting in both directions. And in order to find a horizontal asymptote, we need to let x goes to infinity. 1 over infinity is 0, so y is equal to 1, which is this, is a horizontal asymptote. In order to find the vertical asymptote, we look at the denominator where it becomes 0. At x is equal to negative 2, it becomes 0. So we are going to immediately say, because it's going to give us the infinite limit, because 1 over 0 is going to give us infinity. So as x approaches to negative 2, we get the infinite limit. So we have the vertical asymptote easily. Okay? Alright, so any questions so far? Are you okay with the vertical asymptote and horizontal asymptote? Or are you okay with this picture? Let me get your questions here, because maybe I'm going too fast. Okay. Okay, it's Emre. So let's finish it off. We have 3 pages left. Okay, so here, so look at this function y. Y is equal to negative 8 over x squared minus 4. Our question is, the question would be in the midterm, find the vertical asymptote and horizontal asymptote if they exist. So we know what to do for the horizontal asymptote. We let x goes to plus and minus infinity, right? For plus infinity, so this is going to be a 1 over infinite, which is going to be 0. So y is equals to 0 is a horizontal asymptote for sure. How about the vertical asymptote? For vertical asymptote, we are going to look at the denominator and make it equal to 0. X squared minus 4 is equal to 0 when x is equal to 2 and minus 2. So we have 2 candidates, x is equal to 2 and x is equal to negative 2. These are candidates, but we have to prove that these are really vertical asymptotes. In order to prove that, we have to look at the limits as x approaches to 2 of this f. As x approaches to 2, from the right, one-sided limit actually, let's say x is equal to 2 plus. Let's approach to 2 from the right. Then, let's say 2.1. Excuse me. It's 2.1 squared is going to be just a little bit bigger than 4. So this is still very close to 0. 8 over a number that's close to 0 is going to be an infinite, but there's minus here, you're going to get a negative infinite. So this, you're going to say limit as x approaches to 2 from the right. For this f, it is a negative infinity. Because of that, x is equal to 2 is a vertical asymptote. You have to show that. And as x approaches to negative 2 from the, let's say left. As x approaches to 2 from negative 2 from the left means I have to take the points like negative 2.1. And then if you square it, you get a number that's bigger than 4. So this is positive, there's negative in the front. Take the limit, you get a negative infinity again. So it's an infinite limit, so it shows that x is equal to negative 2 is a vertical asymptote, as well as x is equal to 2 is a vertical asymptote as well. Okay? Secant x. Secant x is 1 over cosine, as you would remember. And 1 over cosine x, cosine would be equal to 0 when what? Cosine pi over 2 is a 0, right? Therefore, we have 1 over 0 is going to give us an infinite limit. So this is a vertical asymptote. Cosine 3 pi over 2 is a 1 over cosine 3 pi over 2 is going to give us an infinite limit. So it's a vertical asymptote. Similar here, similar here. For tangent x, it is sine over cosine again. So cosine is going to become 0 at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, similar to this. So again, we have the vertical asymptotes there as well. Okay, nice example. Both of them has the same denominator, cosine. Okay. That's good enough. That's good enough. Yeah, we finished this section. It's 9:36. I want to show you, let's see, x sine 1 over x, right? It was. Let's go back to that. So I'm going to show that the limit of this is going to be going to 1 as x approaches to infinity using the whiteboard, okay? Let me open this up. Okay, what's this? Oh my god. Almost done. I'm gonna do this example and let you go afterwards. I wanna try my x sine 1 over x, okay? So I'm gonna open up the whiteboard. There's my whiteboard. Okay. And I changed my pen. Maybe I'm gonna write nicer now. Let's see. Keep fingers crossed. I'm gonna show it to you. Oh, what does it say? What is this? Open the app. Just a sec. Okay. Let's get back to. Let's erase this. Alright. Okay, keep fingers crossed. Okay, perfect. Limit as x approaches to plus infinity x sine 1 over x. Okay? The question is, why is this equal to 1? Why is it 1? Anybody knows? Anybody knows this? Can you respond? I'll let you go afterwards. If you don't respond, I'm not going to let you go. Do you know this? How should I do that? Okay. Alright, look, what I'm going to do, look at that. First of all, I'm going to do this change of variables. Maybe I should use a different color here. Sorry. A different, let me use u. Okay, I'm going to do change of variables. So as x approaches to infinity, what happens to u? U goes to 0. Do you agree? Yes. Now I'm going to replace this limit as like this. Limit is, just a sec, for some reason it doesn't allow me, just a sec, I'm going to move this up. Okay, good. Limit u goes to 0. Okay, let me erase this and write it nicer. Okay. Limit u goes to 0. Okay. Sine u over u. This is the same as, I'm telling you, this is the same as limit as x goes to infinity, okay, x sine 1 over x. Okay, is this clear? Because first of all, 1 over x is u, so this is u, but instead of x I can write 1 over u, right? X is 1 over u, right? This is the same. Do you remember this? And this is always 1, right? This goes to 1. We knew that. This is 1. So because of that, actually the answer is 1. Do you understand? I made a change of variable here. Okay, let's go up. Okay, this was the question. This was the question, and we answered it by changing a variable. We just let u to be 1 over x. That's all we did. And we just used x goes to infinity. Whenever x goes to infinity, u goes to 0. And whenever we see 1 over x, we put u. Here is 1 over x. We put u instead. And for x, we just write 1 over u. And that's it. We got that. Okay? That's what I wanted to show you. Okay, that's all. Is this clear for you? Okay, let me get my answers. if it's okay for you, just you can write bye, and then we can just stop here. I want you to write bye, please, in the meeting chat. And I'm gonna do more recording. Take good care of yourself, study really hard. You can ask me questions whenever you want. You can send me through email. You can write it by hand, take a picture and send it to me in the email, and I will answer. Okay? And start working on the homework questions. Take good care. Alright. So I take the attendance according to this meeting chat. Okay. Thank you, Barish. Thank you all. Take care. Bye-bye. You too. You too. Study hard. Bye-bye.